8.5 Lewis structures. Lewis structures are representations of molecules showing all electrons bonding and non-bonding. For writing Lewis structures, there's a few steps. The first one is to find the sum of the valence electrons of all atoms in the polyatomic ion or molecule. If it's an anion, you're going to add 1 electron for each negative charge, and if it's a cation, subtract 1 electron for each positive charge. In the case of PCl5, phosphorus has 5 valence electrons, and each of the chlorines has 7, for a total of 26. Second, the central atom is the least electronegative element that isn't hydrogen. You will connect the outer atoms to it by single bonds, keeping track of the electrons. So far we've used 6 electrons in this drawing, 2 for each of the bonds. Third, you will fill in the octets of the outermost atoms. And again, keeping track of the electrons, we used 6 electrons for the 3 bonds, and we just used 18 more electrons for the lone pair, leaving 2 left. And those will go on to the central atom, fulfilling its octet. If you run out of electrons before the central atom has an octet, then you should form multiple bonds until it does. So this is the case of a double bond or a triple bond. The next step is assigning formal charges. This is something new that you haven't seen before. For each atom, you're going to count the electrons in lone pairs and half the electrons that it shares with other atoms. You will then subtract that from the number of valence electrons for that atom, and the difference is called the formal charge. So if we look at carbon dioxide as an example, oxygen has 6 valence electrons, and the electrons that are assigned to the atom is also 6. So again, we're counting the electrons in the lone pairs. So the oxygen here has 4 electrons as the lone pairs, and we're counting half the electrons that it shares with the other atom. So in this double bond, there are 4 electrons being shared. We're only going to count 2 of them because it's being shared. So we have 1, 2, 3, 4, 5, 6. And that's what we're subtracting from the valence electrons for a formal charge of 0 for this oxygen. And since the molecule is very symmetrical, the other side is going to be the same thing. For the carbon in the middle, we know that carbon has 4 valence electrons, and we're going to subtract 2 from this side and 2 from this side. So subtracting 4, the formal charge is 0 for all 3 atoms. We're going to discuss what that means in just a second. If we look at this orientation, if you were to compare the two and say to yourself, well, does carbon dioxide have 2 double bonds? Or does it have a single bond and a triple bond? Which one of these two is the more stable structure? That's what we're looking at here. So we're going to assign formal charges again. This time for this oxygen, we have 2, 4, 6, 7 electrons being subtracted from the valence for a formal charge of -1. Our carbon has 1, 2, 3, 4 electrons being subtracted from its valence electrons for a formal charge of 0. And this oxygen has 2, 3, 4, 5 electrons being subtracted from the valence electrons for a formal charge of +1. So what does that mean exactly? The best Lewis structure is the one with the fewest charges. Okay, so here we have 3 different structures for a molecule. We need to determine which one we think is the best one. Not only will it have the fewest charges, but it's also going to put a negative charge on the most electronegative atom. And therefore, this is the correct structure because oxygen is more electronegative than nitrogen. Let's go back for a second. So if we go back to the carbon dioxide picture, again, which of these two has the fewest formal charges and also puts the negative on the most electronegative atom? Well, the answer here is obvious, that this one has the lower formal charge. And we've seen this structure before. We know that carbon dioxide does have 2 double bonds in it. Okay, sample exercise 8.6, drawing Lewis structures. Draw the Lewis structure for phosphorus trichloride, PCl3. We're asked to draw a Lewis structure from a molecular formula. Our plan is to follow the 5-step procedure just described. First, we're going to sum the valence electrons. Phosphorus has 5 valence, and each chlorine has 7 for a total of 26. Second, we arrange the atom to show which atoms are connected to which, and we draw single bonds between them. There are various ways the atoms might be arranged. In binary 2-element compounds, however, the first element listed in the chemical formula is generally surrounded by the remaining atoms. Thus, we begin with a skeleton structure that shows a single bond between phosphorus and each chlorine. It's not crucial to place the atoms in exactly this arrangement. We also know that these are 3-dimensional. Third, we're going to complete the octets on the atoms bonded to the central atom. Placing octets around each chlorine atom accounts for 24 of the electrons. Again, remembering that each line or each single bond in our structure represents 2 electrons. And then finally, we're going to place the remaining 2 electrons on the central atom to complete the octet around it. This structure gives each atom an octet, so we are going to stop at this point. Remember that in achieving an octet, the bonding electrons are counted for both atoms. So for practice, how many valence electrons should appear in the Lewis structure for CH2Cl2? So you're going to add up the valence electrons and then draw the structure. Sample exercise 8.7, Lewis structures with multiple bonds. Draw the Lewis structure for HCN. Hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5. The total number of valence electrons is therefore 10. In principle, there are different ways in which we might choose to arrange the atoms. Because hydrogen can accommodate only 1 electron pair, it always has only 1 single bond associated with it in any compound. Therefore, CHN would be an impossible arrangement because it can't form 2 bonds. The remaining 2 possibilities are HCN and HNC. The first is the arrangement found experimentally. We know that HCN does exist. You might have guessed this to be the atomic arrangement because the formula is written with the atoms in this order, or because carbon is less electronegative than nitrogen. Thus, we begin with a skeleton structure that shows single bonds between hydrogen, carbon, and nitrogen. These 2 bonds account for 4 electrons. If we then place the remaining 6 electrons around the nitrogen to give it an octet, we do not achieve an octet on carbon. We therefore try a double bond between carbon and nitrogen, using one of the unshared pairs of electrons we placed on nitrogen, and again there are still fewer than 8 electrons on carbon, so next we try a triple bond, and this structure does give an octet around both carbon and nitrogen, so that would be the correct arrangement. Again, we see that the octet rule is satisfied for the carbon and nitrogen atoms, and the hydrogen atom has 2 electrons around it. This appears to be the correct structure. For practice, draw the Lewis structures for NO plus cation and also C2H4. Sample exercise 8.8, Lewis structures with multiple bonds. Draw the Lewis structure for the BrO3- ion. Bromine has 7 valence electrons and oxygen has 6. We must now add 1 more electron to our sum to account for the -1 charge on the ion. The total number of valence electrons is therefore going to be 26. For oxyanions, these examples and more, the oxygen atoms surround the central nonmetal atom. After following this format and then putting in the single bonds and distributing the unshared pairs of electrons, we have the structure that is pictured here. Notice here and elsewhere that the Lewis structures for an ion is written in brackets with a charge shown outside the brackets at the upper right. Also notice that we have fulfilled the octet rule for all of the atoms. Practice exercise, draw the Lewis structures for these two ions. Sample exercise 8.9, Lewis structures and formal charges. The following are 3 possible Lewis structures for a thiocyanate ion. Determine the formal charge of the atoms in each structure, and then which structure do you think is the preferred one? So we have neutral nitrogen, carbon, and sulfur atoms, which have 5, 4, and 6 valence electrons. We can determine the following formal charges in the 3 structures by using the rules that we've just discussed. So for nitrogen, we would have 5 minus 2, 4, 6, 7, which is a -2. For carbon, we have 4 minus 1, 2, 3, 4, which is a 0 formal charge. And for sulfur, we would have 6 minus 1, 2, 3, 4, 5, which is a plus 1 formal charge. We could do the same set of rules again for these 2 structures. And as they must, the formal charges in all 3 structures sum to -1, which is the overall charge of the ion. So that's something interesting to point out. If you add these all up, you will get a -1 charge, which again is the charge on the ion. We will use the guidelines for the best Lewis structure to determine which of the 3 structures is likely to be most correct. As discussed in section 8.4, nitrogen is more electronegative than carbon or sulfur. Therefore, we expect that any negative formal charge will reside on the nitrogen atom. Further, we usually choose the Lewis structure that produces the formal charge of smallest magnitude. For these 2 reasons, the middle structure is the preferred Lewis structure. So again, this one has too high of a formal charge. These 2 are pretty much the same as far as formal charge goes, but the nitrogen needs to have the negative formal charge associated with it because it's more electronegative. So for practice, you're going to try the cyanate ion, NCO-. Like the thiocyanate ion, it has 3 possible Lewis structures. You're first going to start by drawing these 3 structures, assigning formal charges, and then deciding which one is the preferred structure.